Welcome to this explainer. Today, we're diving into a developing research framework that shifts our fundamental understanding of AI intelligence. Instead of looking at an AI simply as an answer-generating engine, we're going to examine it as a dynamic energy management system. We'll be looking at this through the lens of a recent control-theoretic preprint by researchers Xu and Wei. Our focus today is on understanding AI through what's called the energetic paradigm, and we'll take a calm, objective look at how this model reframes the way intelligent systems actually manage uncertainty. Here's a quick look at our agenda. We'll cover 5 key areas. First, reframing hallucination and failure. Second, local guessing versus global routing. Third, the energetic paradigm layers. Fourth, adaptive warrant calibration. And finally, alignment as structural stability. Let's jump right into Section 1, reframing hallucination and failure. So let's start by clearing up a fundamental misconception. Traditionally, we tend to view hallucination as just a simple failure of knowledge. The AI just generates false information, and that's that. But the energetic paradigm, or EP, offers a much deeper interpretation. Under EP, many AI failures are not simply failures of knowledge. They're actually failures of energy allocation and structural control. A more fundamental failure is when a system outputs unsupported precision, excessive confidence, and unjustified authority. Think of this as a structural imbalance. See, a language model might actually have the correct information, but the system can still fail if it spends too much claim energy compared with the available evidence. It also fails when it applies excessive authority energy compared with its ability to justify an action. Or perhaps it just avoids verification entirely because the local reward favors a fast, complete-looking answer over a careful one. Moving right along to Section 2, local guessing versus global routing. To really ground this theoretically, researchers Xu and Wei set up a minimal formal model. In it, a controller operating under uncertainty has to choose between 4 distinct paths. It can provide a direct answer, initiate information acquisition to retrieve more data before answering, choose abstention where it just defers or refuses to answer, or trigger escalation to a higher cost review channel. Now, there's a really fascinating contrast between 2 mathematical proofs from their paper. Proposition 1 outlines local guessing. It shows that when an AI is evaluated and rewarded only on a local level, meaning it ignores what happens next, guessing actually becomes mathematically rational, even if it's potentially unsafe. But Theorem 1 introduces what they call a global dominance reversal. It proves that when you actually price in the full path of the interaction, the optimal choice flips. Non-answer routes, like retrieving information or abstaining, become safer and mathematically dominant. So what exactly changes the math there? Well, Theorem 1 demonstrates that the safe zone for providing a direct answer mathematically contracts when we factor in downstream costs. And these costs are things like the verification burden placed on the user, the cost of correcting a mistake later, and the consequence-weighted risk. That risk is basically the mathematical difference between an AI guessing your favorite movie versus guessing your exact medical dosage. When the system is forced to account for those downstream effects, guessing just isn't a viable shortcut anymore. Let's look at Section 3, the energetic paradigm layers. We can map this exact mathematical routing directly onto the overarching energetic paradigm framework to better understand the system's internal state. The foundational layer here is evidence energy. Instead of just asking what the AI knows, this quantifies the actual structural support currently available to the system. We're talking about verified sources, reliable retrieval mechanisms, and statistical confidence. It's the bedrock that any response has to be built on. Sitting right on top of that evidence is what we call claim energy. This is the level of specificity in the AI's output. It can range from a very broad conditional explanation all the way up to a highly precise, definitive claim. The core rule here is that an AI becomes structurally unstable and essentially fails when it spends too much claim energy relative to its available evidence energy. And finally, there is authority energy. This represents the degree of action guiding power in the AI's tone, moving from a simple objective description to a direct instruction or recommendation. Under this paradigm, authority energy has to remain strictly proportional to both the underlying evidence and the potential downstream consequences of that action. This all brings us to the central concept of energy matching. A reliable AI system should always match the strength of its output with the strength of its supporting structure. It's pretty straightforward when you think about it. More evidence allows for higher specificity, stronger conclusions, and greater authority. On the flip side, less evidence strictly requires narrower claims, conditional language, and additional verification. Remember, A statement might contain entirely correct information, but it is structurally unstable if the output exceeds the available support. Which leads us naturally into Section 4, Adaptive Warrant Calibration. Because keeping this energy match isn't just a static, one-and-done process. The EP framework visualizes intelligence as an adaptive system governed by an adaptive calibration loop. It has to continuously evaluate evidence availability, assess its own uncertainty alongside the consequence exposure, adjust the cost and usefulness of verification, and then carefully calibrate its decision authority before taking any action. This builds directly on Theorem 2 from the source paper, which models an ordered threshold controller. Basically, it explains that fixed answer strategies are structurally fragile because they treat every single situation as having the exact same energy condition. The energetic paradigm instead views true intelligence as an adaptive control system, one that continuously adjusts its verification effort, its information resolution, and its decision authority in real time based on changing conditions. Bringing us to our final section. Part 5, Alignment as Structural Stability. Ultimately, looking at AI through this control theoretic lens really reframes our entire approach to AI alignment. Alignment isn't only about programming human values or adding restrictive prompts to a model. A much deeper question we have to ask is, can the AI maintain a stable relationship between its capability, its available evidence, its local incentives, and the global consequences of its actions? So the EP perspective treats alignment fundamentally as a stability problem. True structural stability requires active mechanisms designed to prevent unsupported precision, excessive confidence, and unjustified authority. Even if a statement contains completely factual information, it remains structurally unstable if the output exceeds the available support. If a system can't balance these elements, it simply can't be considered reliably aligned. As a developing framework for exploration and research, EP offers a rigorous way to evaluate system safety without overstating where the technology is today. To wrap up this explainer, I want to leave you with a concise summary from the text. The energetic paradigm provides a systems perspective for understanding AI behavior. Instead of viewing intelligence only as generating correct answers, it examines how intelligent systems regulate information, confidence, authority, and action under changing conditions. So the next time an AI gives you a highly confident answer, it's worth asking, does it actually have the energy to back that claim up? Thanks for joining me for this careful look into the mechanics of AI control.